In Lesson 4.5, you will solve quadratic equations by finding square roots. In these examples, we're going to simplify the square root expression. In the first one, we're going to simplify the square root of 500. To do that, we want to look for a perfect square factor of 500, the largest perfect square factor of 500, which is going to be 100. So I'm going to factor 500 into 100 times 5. And then I can use the product property of square roots and take the square root of 100 times the square root of 5. Now the square root of 100 is 10 because 10 times 10 is 100, and that's what we're looking for, two factors alike that will give us that radicand. But I can't simplify the square root of 5, so the result is 10 times the square root of 5. In the second example, we're going to use the product property of square roots again, only this time we're going to go the other direction and we're going to put those factors 12 and 6 underneath the same radical. And so when I multiply, I have 3 square roots of 72. And now again, just like before, looking for the largest perfect square factor of 72, I find that that's going to be 36. I can factor 72 into 36 times 2, and then use that product property of square roots again to take the square root of 36 times the square root of 2. So the square root of 36 is 6, and 6 times 3 is 18. So I get 18 square roots of 2 when I simplify. Okay, in this third example, we can use the quotient property of square roots to simplify, because we can take the square root of the top divided by the square root of the bottom, and the square root of 25 on the top is 5, because 5 times 5 is 25. And we can't simplify the square root of 3 in the denominator, but we can't leave a radical in the denominator of a fraction, so we need to rationalize the denominator now, or get rid of the radical in the denominator. And to do that, we need to multiply this fraction by a form of 1, so we don't change its value, and that form of 1 is going to be the square root of 3 over the square root of 3. And then we'll multiply tops, 5 times the square root of 3, and in the bottom we can use our product property of square roots to write that as the square root of 9, and we know that the square root of 9 is 3, so we want to leave this fraction, this expression, as 5 square roots of 3 divided by 3. Okay, in the fourth example, we are going to have to rationalize the denominator again, only this time we can do it in a different way. We can use another method where I would first multiply underneath this radical by a form of 1, so that I don't change the value of the fraction, but I change what it looks like. And then multiplying, I have 22 in the top and 121 in the denominator. And now I can use the quotient property of square roots and write separate square roots, the square root of 22 divided by the square root of 121. The square root of 22 doesn't simplify, there's no perfect square factor in 22, and the square root of 121 is 11. So we're able to simplify and rationalize the denominator. Okay, in the last example here, we need to rationalize the denominator. So we're going to use the conjugate of the denominator. We're going to multiply by a form of 1 again. 5 plus the square root of 2 over itself. That's the conjugate of 5 minus the square root of 2. So we'll multiply by this form of 1 to rationalize the denominator, or get radicals out of the denominator. So in the top we'll distribute 4 times 5 is 20. And 4 times the square root of 2 is 4 square roots of 2. In the denominator, we're going to distribute. We'll have 5 times 5, that's 25. 5 times the square root of 2 is 5 square roots of 2, but when we start over, we have negative the square root of 2 times 5. That's negative 5 square roots of 2. So positive 5 square roots of 2 and negative 5 square roots of 2 sum to 0. We have no middle term. And then negative the square root of 2 times positive square root of 2 is going to be negative the square root of 4. And the square root of 4 is 2. So in the denominator, I have 25 take away 2, which is 23. So this is the way I would leave my answer, with the denominator having no radicals. Okay, in the next two examples, we want to solve the quadratic equation by taking square roots. So if you look at this first quadratic equation, there's no x term in this equation. So that means we could get x squared alone. So to do that, I'd first subtract 3 from both sides, getting my x squared term alone on the left. Over here I have negative 9 minus 3, that's a total of negative 12. And then divide both sides by negative 5 to get x squared alone. So I'm going to have x squared is equal to 12 fifths. And now to get just x, I want to undo this power, so I'm going to take the square root of both sides. When I do that, the square root of x squared is just x, but I'm going to get two solutions, plus or minus the square root of 12 fifths. And I'm going to have to rationalize that denominator in my answer. So I'm going to rationalize again underneath the radical. I'm going to multiply top and bottom by 5, so that this becomes plus or minus the square root of 60 over 25. And using that quotient property of radicals, I can take the square root of 60 over the square root of 25. Okay, now we need to simplify the square root of 60 if possible. And the factors of 60 are 5 times 2 times 2 times 3. It looks like the perfect square factor in 60 is going to be 4. So I'm going to factor 60 into 4 times 15. I can take the square root of 25 in the bottom, which is 5. And so using that product property of square roots again, the square root of 4 in the top is 2, and I'm left with the square root of 15, which has no perfect square factors. And in the bottom denominator I have 5. So my two solutions to this quadratic equation are, and I'll put them in a little solution set, negative 2 square roots of 15 over 5 and positive 2 square roots of 15 over 5. Okay, in this second example, I can see that I have a quantity squared that includes my variable x. So to solve this equation for x, I'm going to leave that quantity squared. I'm going to get it alone by dividing both sides by 3, so that I have x minus 2, the quantity squared, equal to 7. And now I'm going to undo this power again by taking the square root of both sides. So the square root of this binomial squared is just going to be one binomial, x minus 2. And on the right hand side, I'm going to get my two solutions, plus or minus the square root of 7, because I'm taking the square root of my variable squared, which is going to give me two solutions. And now solving for x, all I have to do is add that 2 to both sides of the equation. So I get 2 plus or minus the square root of 7 for solutions. And I'll separate them again so that you can see 2 minus the square root of 7 is one exact solution, and the other is 2 plus the square root of 7. Okay, in our last example, we have the tallest building in the U.S. is in Chicago, Illinois. It is 1,450 feet tall. How long would it take a penny to drop from the top of this building? So we're going to use the falling object model to solve this problem, which is h equals negative 16t squared plus s, where h is the height of the dropped object in feet after t seconds, and s is the object's initial height in feet. So using h equals negative 16t squared plus s, I want to substitute in the 1,450 feet for s because that's the initial height that this penny is dropped from, and h is going to be the height when it hits the ground, so that height is going to be 0 when it hits the ground. So we'll substitute in those values and we'll solve for t. Okay, so we can use our method of taking square roots by getting t squared alone. There's no t term in this quadratic equation, so we want to get t squared alone. So I'm going to subtract 1,450 from both sides to get my t squared term alone, and then divide both sides by negative 16 in order to get just t squared. And now I need to undo that power. So I'll take square roots of both sides. The square root of t squared is t, and now I know I'm getting two solutions plus or minus the square root of 1,450 over 16. But time will never be negative, so for this problem I'm just going to choose the positive value and I'm going to approximate it using a calculator. So when I put in 1,450 divided by 16 and take the square root of that result, I'm getting an approximate time of 9.5 seconds. .5 seconds for that penny to drop from the top of the tallest building in the U.S. in Chicago, Illinois. Include with your notes of this video guided practice problems 1 through 19 found on pages 266 and 268 of your textbook. That should read guided practice problems 1 through 19 odd. Do the odd problems only.